Okay, thank you, Abhi. So, hi, good afternoon. I really appreciate you coming here. I'm going to talk about unstructured data acceleration, which is basically accelerating Hadoop using RDMA technology over fast networking. So, I hope you read that fast. Now, a little bit about us. So, how many of you have heard about Mellanox? Just raise your hand. Okay, that's good. How many of you haven't heard about Mellanox? Okay, no abstaining, right? So a little bit about Mellanox. I thought it's good stuff to get you into the picture of things that we've been doing. So Mellanox started in 1999 as a semiconductor company doing silicon for NICs that we also call the ACAs. Those are NICs for InfiniBand, as well as switch silicon. And from that we evolved into a little bit more than just silicon for NIC and the switch. We're doing also systems. We're also doing the adding cards for the NICs and different form factors. We're also doing the switches, system switches. We've been doing a lot of stuff over InfiniBand, but recently we also entered into a full Ethernet also based solution. So we have both InfiniBand and Ethernet, and actually our hardware is capable of running over InfiniBand and over Ethernet. We call that VPI. Same hardware, just configure the protocol at runtime, or just even auto-sense it. So on top of those infrastructure, what we're doing also is to develop acceleration software. Things like VMA. VMA is messaging accelerator, basically a transparent middleware that is providing socket interface, and every socket-based application can just run on top of that and leverage very high throughput, low latency, and high message rate on top of either InfiniBand or Ethernet. And that's about VMA. It's all about transparency to the application, but accelerating it by the underlying implementation. Another example is VSA, which is storage acceleration. It's basically a cache target storage that is doing block storage accelerator that is placed between host and storage. And last, we also have management suite that can look at the entire fabric, reconfigure it, allow monitoring, show the topology, and so on. So that's pretty much what we do. And a little bit about our hardware at the NIC level. We have a lot of benefits that we provide because it's not regular NIC, it's not just a plain layer 2 NIC. We also provide what we call I/O channels. I/O channels is basically the ability of taking a NIC and carve it into multiple channels and export those channels up to the applications. So by that I mean that applications can directly access the hardware and send, receive data, and so on. And that can run in a regular environment where you have different processes, or it might as well just run in a virtualized environment where you have process inside virtual machines, inside a hypervisor domain. Basically, you just virtualize the IR service and the hardware performs the segregation between the different ingredients. It's all about efficiency, so we care about high throughput, and we provide that with with a set of services that really accelerate the performance, things like RDMA, kernel bypass, and full transport offload. So all the segmentation, reassembly, retransmission, all of that happens in the hardware. And again, the interface can run over a standard interface. It can run over RDMA, over Ethernet, or over InfiniBand, and that's what we call VPI. You just configure the hardware at runtime. So this one showing like the example stack that has the regular interfaces on top, and they can go to the IB transport, which is the RDMA transport for send, receive, and RDMA. Goes to a network layer, and then it can just go down into IB link layer or Ethernet link layer, and basically it's transparent to the software. The very same software can run on top of InfiniBand or Ethernet. And basically sometimes you just code your application down to the InfiniBand interfaces or the RDMA interfaces. And sometimes you can just use a middleware, things like the VMA, that really abstracts everything from the application, and you keep the application unmodified, but rather accelerate things under the hood. This is what we're doing in UDA, for example. So this is an example of how our NIC looks to the application. Basically, you have queue pair, QP. This is a set of a send queue and a receive queue. An application can really post jobs to the send and to receive queues. Whenever they complete, they generate a completion queue. An application can poll and see what's the progress on the status of the jobs posted to the hardware. with a single work queue element on the send. You can send, for example, 2 GB, or you can actually access remote memory just over the network. So you can read or write from remote memory with just a single operation without even requesting any intervention from the remote node. So basically, this is the model, and basically the QPs are unlimited by the amount of them, so you can really accelerate up to about 16 million different channels, export them to the different applications, and they can really send and receive stuff through the hardware. And last thing here is like an example of how you can leverage RDMA to implement an RPC. On the left-hand side, you see a client and a server, and let's say that we want to do a simple RPC that will get the buffer from the server. So basically what you do in the software, you trigger a send work request from the client and say, okay, here's the RPC request. And then what the server will do is the server will do an RDMA write. It will DMA the buffer from the server buffer directly to the client buffer. So this is very efficient. You can really transmit like that megabytes or gigabytes of data. Everything goes on the PCI from one memory to another. It's all very efficient. Hardware does all the retransmission and segmentation or whatever needs to be done. At the end, the server will send an RPC completion, and the RPC is done. So that's pretty much how we accelerate different applications, especially if you look at things like Hadoop underlying the implementation. At the end of the day, does some kind of an RPC, whether we just, for example, retrieve a file, we can use the same mechanisms and work very efficiently because the hardware will do all the transfer, and we don't need to do some extra copying between user, kernel, and those kind of things. It all goes from user mode, from the application buffer into the remote application buffer. So a little bit about where we are in the big data. So obviously everybody here is because of the big data. And it's like a multidimensional problem of things that are, a lot of data being collected from so many places, and it's just growing a lot of unstructured stuff, running at different kind of things and different kind of data. And basically where Mellanox comes to play is when you want to analyze this big data, there are two things that we care about, especially here in the Hadoop. We look at velocity and volume. So what we try to do in UDA is really to accelerate the performance of running, high volume data sets with large input data sets, with large intermediate and final data sets. What we play with the velocity here, just to accelerate things so they can run faster and you can really save on the performance or get just results much faster. On the variety side, we also try to accelerate other applications, like memcached, for example. Generally speaking, with VMA, any socket application can get the benefits of the hardware for that. Okay, so I think going a little bit about the networking, and when I say networking, I refer to everything like starting from the host side and continuing through the different switching infrastructure. So basically, can we really benefit from a better network? I mean, Hadoop has been developed, under some conditions, right? There were like a slow network, it's given, it's not very efficient, you have packet drop retransmission, it's very slow link in the pipe. But now we're talking about slightly different network, and we're talking about some game changers that are happening, and I'm going to talk a little bit about that, trying to say, yeah, we need a better network, and with a better network we can do much better stuff. So let's look a little bit about what happens in the Hadoop platform, right? Everybody knows that you write the mappers and you write the reduce code, and this is the code that will be, kind of executed by the cluster, whatever size it is and whatever data there is. So basically what happens, those are spawned and you don't really understand what's happening, but under the hood, what happens is that, data is read locally from a disk, is being fed into the mapper. This is typically local because of the Hadoop scheduler to do it quite right. And then the mapper processes the data and creates the intermediate data set. What happens now, everything is ready to be shipped to the reducers, but it has to go through the network. So that's the first networking phase where you kind of shuffle all the data. So things from all the mappers go to all the reducers. And in several cases, when you run huge data set, this is the amount of data that has to go through the network. And this is traffic that goes from all the servers to all the server. The ballpark can be huge for large data sets, and that goes through the network. Once you finish the shuffling phase, you kind of merge and sort the data from the different places. You group them by the keys, and then you feed it into the reducer. So the reducer will process the data and create the final data set that will be saved to local disk. But I'm not done yet because there is yet another phase. So maybe not in this TerraSort benchmark, but definitely in production environment when you really want to make sure that your data persists and your data locality is improved, and you do that with replication. So if you look at what happens when you analyze a huge data set, you have to traverse it about 3 times through the network. 1 time in the shuffle phase and 2 times in the replication phase. So those are 2 network intensive phases that this is the kind of things that we want to accelerate with UDA. So I mentioned that there are some game changers here, and we can see 2 things, okay? Let's start with the fact that it really makes sense to have the I/O available at the server matching the I/O coming from the disk drive, right? Because at the end of the day, you read a lot of data from the disk, you write it to the disk, and then you need to pull it out of the machine and put it back to the machine. So basically, the right setup or the right configuration would be to really match the I/O speed of the disk to the I/O speed of the networking that you have in the cluster. And I'm not even talking about peak scenarios where you have many guys that are sending to a single guy and so on. Those really mean that you need to a little bit over-provision the network. But at base minimum, you really have to match the I/O speed of the server. So if I look at the top graph, I just put some highest ranking things, but I tried to put several configurations that make sense in a typical Hadoop environment. Of course, the SATA would be the right example. So if you have, just look at the 3 lines. The lines would be the low line. The red one is 1 gig, and then the yellow is 10 gig, and the blue one is 40 gig, equivalent of a network. So look at the first example, single SATA drive, that's fine. If you have a single SATA drive, you have 1 gig, you have matching bandwidth, you're all fine. But what we see is that people install more and more SATA drives because of 2 things, because of performance and because of capacity. So whoever cares about performance, you can really see that in the case of 4 SATA, you really pass the 1 gig at the peak times. And if you're using 12 drives, you can even go beyond 10 gig. And really means that you really have to provision the network accordingly. I gave you some other examples, the SSD, which might be a little bit something to talk about in the second graph, but basically SSD have a good performance, both on peak bandwidth and also on random access, which might be more suitable here. So I just put SAS drives and PCIe drives, depending on what you choose. Definitely you need beyond 1 gig, and for some cases where you install multiple disks, you want to really get a good performance, then you need to go 40 gig and beyond. So what happens in the SSD, and we really think it's coming, and you can look at the bottom graph and you can see the blue line showing average sales price for SSDs going down, especially if you look at the red line, which is calculating average sales price per gigabyte. It really goes down throughout the years. And if you look at the bars, they're showing the average capacity, which is growing. So those are 2 good things for Hadoop, right? You have increasing capacity, so you can analyze larger problem data sets, and you have decreasing price per gigabyte. So overall, it looks promising. It's not happening yet, but it is going to happen really soon. And I think those kind of things, that placing a lot of drives and the decrease in the SSD pricing, those are the things that will drive much more need for faster networking. And we're talking about 10 gig and beyond. So, talking about the networking, so here I draw an example of the networking that we build in Mellanox. So that will be a classical InfiniBand network, but we're working to bring the same technologies to InfiniBand, from InfiniBand to Ethernet as well. You can see the switches are connected in a class or a factory topology, whatever you call that. This topology can really scale. If you look at those, the server down there are connected to a top-of-the-rack switch, and those top-of-the-rack switch are connected to core networking. So you can have balanced east-to-west traffic, and it's like a non-blocking topology from every server to every server, regardless whether they're physically located in the same rack or across rack, or you can even customize it to whatever blocking ratio you like. The networking that we provide today supports up to 40 gig network speed on InfiniBand and Ethernet, and they give even go to 56 gigabit in InfiniBand this year. The idea is that in terms of capacity, you really want to match all the I/O bandwidth that is available on the server. So whenever you have on the server all the disk or CPU computation that you want to transmit to another server, you have it all. It can go through the network. So let's face it then. So another thing about the networking, that's a new trend that is happening now, is having a lossless network. Lossless network is much more efficient in terms of avoidance of retransmission and those kind of things. So when you have a fast network, you can really reduce the cost of the network and make it much more efficient with the losslessness capability. And beyond that, we even push stuff into the HCA or to the NIC at the host level, where we offload as much as we can from the CPU. So thus we leave a lot of room for the computation on the server. And we offload everything that has to do with communication on the NIC. So we talk about reduction of CPU utilization. So jobs that are really heavy on the CPU load, we can just relieve some of the CPU cycles and get the job faster. And overall RDMA, zero copy operations, all of them reduce the CPU utilization and improve the runtime. And also key ingredients to driving networks at that faster speed. So let's talk about UDA plugin and how it comes to play here. Okay, so UDA is the unstructured data acceleration. It's an open source Hadoop RDMA plugin, and basically what we're trying to do is the UDA plugin is to plug into the Hadoop platform, keep the unmodified application there, and accelerate the transmission of the map output file to the other side using RDMA. So in a nutshell, we're talking about the plugin architecture. So it requires absolutely no change to the existing Hadoop application. So just you plug in this UDA and everything just runs faster. Unmodified application, open source, and basically you kind of enable that to an XML configuration. So, if you want to set it, you do it on a per job basis or per site basis. You just choose if you want to run it or not based on the regular XML configuration. And obviously there are some other tuning parameters that you can choose from the XML configuration. With the plugin, we're doing essentially two major things. The first thing is efficient map output file transfer over RDMA. This is basically the shuffling phase of Hadoop. It supports InfiniBand or Ethernet. We just wrote it once, but it transfer InfiniBand and Ethernet because everything is agnostic to the underlying layer 1 technology. And it supports zero copy, transport, offload, or kernel bypass, which are all saving CPU, and I'll show you some performance that backs this up. The other thing that we're doing in the plugin is to accelerate the merge sort. So the existing implementation really assumes a slow network and some characteristics that are no longer stand when you're talking about the fast lossless network. So basically with that paradigm, we're able to do different merge sort algorithms that I'll show you a little bit about that. And just leveraging the fact that it's a fast network, you can keep the data where it is, and if you need it, it will come back to you as fast as you need it. So you can look at the right-hand picture. You can see the Hadoop platform itself with traditionally go on the right-hand side with the socket library in the kernel and all the transport that is processed in the kernel with a lot of copies and all of that. And if you go to the left-hand side, it has the RDMA plugin that goes directly to the hardware. So a little bit about how it works in terms of software architecture. So basically, that's the classical Hadoop. You have, you have a job tracker and a task tracker on the same node, and the task tracker can spawn multiple map tasks and multiple reduce tasks on the same machine. Then basically, there are mappers and reducers on all the machine, and you need to exchange data between them using either the existing implementation or using the UDA. Basically today the data is being exchanged over HTTP. There is an HTTP server, and the user task will call an HTTP client and fetch the data with it. What we did in UDA is basically to develop a daemon. It's a UDA plugin, it's a daemon that just runs on the machine as well. It's written in C++ because that's a way for us to utilize better the RDMA capability, the zero copy and all of that. So it runs like a plugin a daemon, and it basically has two parts. The first part is the MOF supplier. That's the map output file supplier. This is the component that replaces the HTTP server. So basically, it's going to serve requests that's saying, okay, I need a file. Those are the RPC requests that we talked before. So I want a file, so it gets a request and transmits the data back. The other component is the net merger. Net merger replaces two things. It replaces the HTTP client that fetches the request, and it also has a merging capability. So it basically does the merge for all the data coming from all the mappers. So look at the data flow, it pretty much looks like that. So data flies from the map task down to the RDMA server. So maybe just more accurate, when the map task finishes, it writes the data into local disk, and then the RDMA server is ready. Whenever there is a request coming in, it can serve the data. The reduce task is aware of a mapper that finished, and it signals the net merger here. And net merger knows to go to all the mappers and request the data via RDMA. So this is the RDMA client talking to the RDMA server. And once you have enough data, then you can start merging and pass streaming data up to the reduce task. So that's how it looks on the data path. And basically, if you want to look from timeline, what's happening under the hood here. So let's look a little bit about the timeline, what happens when you run a Hadoop job. So basically, you have the map stage where all the mappers are spawned and running, and they're doing the mapping, and whenever a mapper is done, it saves its split into the local storage. So that hasn't changed at all in our implementation. The vanilla Hadoop shuffle merge algorithm works like that, right? Whenever a mapper is done and it has a file, you start shuffling. So this file will be taken and transmitted to all the relevant reducers, and you kind of shuffle and shuffle and shuffle as long as mapper finish. You move the data down to the reducers, and when you have enough files that you got from the reducer, you start merging them. You merge a file, another file, and another file, and this is an iterative process that you keep merging forever until the last mapper is done. Then you do the final staking of the merge, then you have the full merge file, and then you pass that into the reducer. As you can see, this process involves a lot of disk I/O, and when you're doing the merging, iteratively you're reading and writing more than just the overall that you need. You just keep reading and writing to the disk and merging all the stuff, especially when you're talking about large jobs. The new shuffle and merging algorithm that we're doing is leveraging the fact that the network is really fast and you can really retrieve the data much faster. So instead of doing a lot of stuff on the reduce side, we just keep the data where it is, and we try to avoid an extra I/O, an extra access to the hard drive. So what we basically do is we say, okay, we don't need all the data, we just need the headers. Okay, let's go fetch the headers from where they are. Header is just the beginning of what you needed. And then with the header fetch, so as long as mapper is finished, we fetch the header, but we don't do the merge because we want to do a final merge once and for all. The second stage that we're doing, once this last mapper has done and we have all the headers there, we start merging. So basically the merge is simple. You look at all the headers, find the smallest value, pass it on, that's the first one, and then find another smaller one, pass it on, and so on. So that's how we do the merging. And basically it looks like we're doing something streaming, right? We keep on getting the lowest one and it's ready to go to the reducer because we're looking at the entire data set. And we can just pipeline it and pass that to the reducer. So basically, the reducer now in the UDA implementation can really get the data while we're still shuffling and fetching data from the remote machines. So it's much more efficient, and again, the assumption here is that we have a fast network and we can really retrieve data very fast and very efficient. We just keep it where it is and we just fetch it. We just go all the way to the reducer without an extra I/O access on the drive. So some performance results that we were getting on a small cluster, we were running TerraSort benchmark, and basically wanted to show the linear scalability. That is a very typical thing for Hadoop. This is one of the nicest things about Hadoop, that you can add more and more nodes and increase the problem size, but you still get the same runtime. So what you see here is a TerraSort that we were running 16 gigabytes per node. So when we add more nodes, we add more data to sort, and that's the expected results, that the execution time will stay fixed. That's linear scalability. So you can look at these three lines. The left end y-axis shows the execution time. So you can look at the yellow line and the red line. The yellow line shows the 10 gig performance, and the red one shows the 1 gig performance. And you can see that they're pretty much in par. The 1 gig and the 10 gig are pretty much in par. They're doing this high execution time, and you can scale from 8 node to 12 node. They're getting the same time. The thing that is being actually shown here is that it's not enough just to have a fast network. You also have to have an efficient network, and that's with the UDA plugin. So the blue line shows the execution time for the UDA plugin. You actually show about 40% improvement when you're running UDA over this number of nodes. And the dotted line is referring to the right-hand side y-axis that's showing the improvement. So we're talking about 40% improvement that we're getting by running TerraSort over up to 12 nodes here in this example. Those are all initial results, and we keep running and improving the software. Another nice thing to look about is the actual CPU utilization. And there are two nice things to see here in the graph. So in the graph you see the execution timeline on the x-axis, and you see the overall CPU utilization of the cluster. So if you have a 1 gig run, this is the red line, then you really see that job takes longer. So compared to the blue line, which is UDA, you see job takes longer. So this 40% improvement, this is sometimes else. You can just use the cluster for something else. You can run more jobs finish faster, and you can utilize better the CPU. Or if you don't need, you can just borrow off the service. The other thing you can see that throughout the runtime of the process, because of all the offloading, you can really see a reduced CPU utilization. So overall computation really required is very minimal. So when I'm talking about TerraSort benchmark, it's basically all about just running, and the mapper and reducer are pretty much empty in a TerraSort. Basically, if you really want to analyze big data, you need to put some stuff into the mapper and the reducer that will do some significant work. And this is where it gives you room for the CPU. When things are offloaded, you get a lot of more CPU. So even jobs today that are CPU intensive, you can relieve some of the CPU by just running UDA and get much better, much shorter execution time. So that's pretty much it. I'd like to give some short summary and obviously something to think about, because this is all interesting stuff. So a few words about UDA. It's an open source plugin. It's accelerating today the shuffle merge process over RDMA. It reduces the CPU utilization because of RDMA transport offload and all those kind of things. It's optimized for high-speed networking, and all the algorithms there are tuned for running over fast networking with a new paradigm, fast and very efficient networking. And we've demonstrated 40% improvement for the TerraSort benchmark. So that's about UDA. There's a beta that is available today to Mellanox side. And basically we're planning next release that will include pretty much those features that we're going to rebase to the 0.20.203 Hadoop version. We're going to improve the support for multiple spindles to work much more efficiently in pipeline. And we're going to improve the merging algorithm for better scalability and a lot of stabilization, because this is all new code that we're optimizing. And just before I go, something to think about. I'm just trying to put together things, but still it really makes sense that something to think about when we go. So there's a new paradigm shift in the network. It's not a bottleneck anymore, and it has new characteristics. And this is all interesting because you have like full ability to go from one CPU to another. You can just go very efficiently. You can match all the I/O speed from the server. You can put it in and pull it out of the network with a very efficient network, with very low latency, with very high throughput. So, with those tools, can we innovate? Can we really find a new solution, a new alternative to solving the big data problem? So, what I show is the first thing, there's a lot of room for innovation with those technology to solve the big data problem. So, that's all. I'll be happy to take questions. Yes? Is there, I cannot hear. Is there a mic though? Is there a microphone? Yeah, just shout. Yeah.
Yeah.
If I have a mixed environment, and I'm just trying to establish the Ethernet environment,
Yeah.
and also remind me, are any going to come from Java taking and running this heterogeneous environment?
Okay, so the question was what happens if you have an existing Ethernet environment and you want to add also InfiniBand environment or running some heterogeneous environment. So that's a good question. Generally speaking, we have technologies that enable bridging from InfiniBand to Ethernet, and we have there are some ways you can merge the stuff. You can also look at that in the context of new installations, and this technology also works on Ethernet. So if you want Ethernet, it can also work there. Basically, you get better performance as much as the bandwidth in the network is faster. But this is doable. It's possible to connect with different networks. And we're also working on better technologies to enable that as well. Any more questions? Yes.
So you talked about pipelined app and release. Is that open source? Is that available for download? Or, I mean, it seems to be a new addition to app release.
Yeah, so those are new algorithms for mapping reduce. For the shuffling, it's basically part of the plugin. And you can get an evaluation for the beta. I have the link here. Just log in and request the evaluation code, the UDA. Any more questions? All right. Thank you very much.